Hello everyone and welcome to this 7th week of the second module. We're going to end this week by adding some subfracture pieces to the already cached sim, and also we'll create a debris system to it. As usual, I'll try to stay procedural on every step, and although this makes the workflow creation a little bit advanced, I can assure you it's worth it. Heads up before starting this, be sure you completely understand what transform pieces node is doing, because we are going to use it a lot. And so maybe read the Houdini documentation, where you can find some very useful examples here. Spend some time playing with it, or just see the previous weeks. That being said, let's get to it. Let's start by caching this simulation to disk, because I don't want to waste my time waiting for this simulation to be done every time I have to transform or to the high ratio or to add more elements to it. So I'm gonna drop down a file cache here. Let's call it sim house, and I want to add some custom parameters to make the caching easy. So let's go to the parameter interface, and I'm gonna add 3 strings. Let's put it on the top of this interface, and let's press D 2 times to duplicate this. The first one, I'm gonna call it the type, and this is gonna be it could be like the simulation, geometry, BDB, etc. The second one, I'm gonna call it element, and this is the element name that we are saving, in this case the house. And the third one would be the version. So let's apply this, and let's reference these strings house and 001 after the global variable heap. So I can copy parameter and paste it here, slash copy the element and paste it here, slash and copy the version, paste it, and let's grab the name of the node. We can use $OS, or we can also use OP name of this node. I want this to be in the whole frame range, so let's set this to $4 PGOSC. Okay. So now we are gonna create this new folder and these new files inside this week 5 sim house version 1 sim house. So I'm gonna press save to disk. I'm gonna give it not 240 but maybe 100 frames, and I hit pause. Okay, so this is already finished, so let's take a look at the outcome of this cache. As I said, this will create automatically the folders we need, and we can see we have 100 frames sized 1.33 gigabytes. We can optimize hugely this outcome, this cache, by importing just not the geometry, but the the create points to represent objects. Also, note that we are saving all of these attributes, and this is going to take this needs some space to be saved. So let's create an attribute rename, and I'm going to use this keep attribute option. As you can see, if I delete the star, all the attributes are going to be deleted. So I'm going to say which attributes I want to keep. For example, velocity, maybe angular velocity, pivot, orient, and name. And yeah, I think this is fine. So let's save this again. override this simulation to compare the size. This is done again. It took me like 1 minute and 30 seconds. So let's take a look now at the size of it. As you can see, we have gone from 1 gigabyte to 23 megabytes. So this is a huge improvement. And what we're going to do with these points is to transfer the transformation matrix, the orientation, the pivot, to either the proxy geometry or the high-res geometry. Before continuing, I told you that I want to art direct our subfractures, and this means that I want to generate subfractures on the pieces where they have impacts. So to do so, I want to save along with this file cache the impact points. So let's drop down a .import records. I'm gonna call the sim house. If you remember, we have to write impacts here and here. And this is gonna create a point for each impact that it can detect. As you can see, we have a bunch of different attributes here, but the ones we're interested with are just the impulse and the object name. So I'm going to use again the attribute rename, and I just want to keep the impulse and the object name. We'll use these attributes to drive the areas where we want to create new subfractures, and also we can select what kind of element we want to break with the object name. Cool, so in order to have control of what points are belonging to the simulation and what points belongs to the records, let's create a group, point group, and let's call it records. And this will be a point group. Now we can merge with the main simulation, and let's save this again. Okay, so the cache is already done, and as you can see, the size is also super low, super convenient. And along with these points, we have the attributes we will later on need. Let's go on and create the subfracture workflow by going to the object level. I'm gonna create a new object. Let's call it house subfractures to be organized. Let's dive in, and I'm gonna call some nodes here. First one, we'll start with the wall, so I need the wall. I need another one. I'm gonna call the simulation, the points, and that would be it. So first, let's split the simulation points from the record one. Let's say invert selection, and now from this output we are getting the simulation points, and from this one the records. So let's store it here, saying that this null will contain the record impacts. And now you can see we can drive the transformation of these static objects using a transform pieces. So let's connect this first input here, second input here, and if I hit play, cool. I also, this time I want to copy the template attribute because I want these pieces to inherit all these orient, pivot, name, impulse, all of these attributes. So let's turn this on and write a star here. And here we go. Okay, next step is to unpack this geometry. Let's transfer all these attributes to the unpacked geometry. And now what I want, and since I think I have the density attribute, which, if you remember, is the attribute that conveys all the impact areas. I want this attribute to be promoted, so let's promote this attribute from primitives to points. Now, here you can get rid of the first gotcha. A gotcha is some step where it's super difficult to debug, and it can lead you easily to one mistake. So let me show you something. If I go back here, let me go to the pack geometry, and I want to take a look at the pivot attribute. Take a look at this. This is the pivot values of the first frame, the frame 0. And if I give one more frame, you can see this is changing, but on the next frames, unless the piece is moving, they will have the same values. And this is going to mess our geometry when we transfer the movement, the orientation and transformations. And why is this happening? This is happening because this is coming from the simulation, and at the first frame, the simulation takes the pivot of the geometry we are sending from the input, but at the second frame, the simulation is taking the pivot of the geometry representation, and it's gonna keep working with this second pivot until the end of the simulation. So what we can do after the unpacked, for example, is just to time shift this one frame. I'm gonna write here, take the start frame and add 1 unit, and then copy it to the original geometry. So attribute copy to this. This is the source, and I want to copy the pivot. Now I will always have the same pivot, which is 1 frame forward. Cool. So the workflow is the following. We want to fracture these pieces based on the density attribute, because remember, we don't want the same amount of detail on the moving pieces than on the static ones. And then we're gonna active all of these small pieces using the DOP import record information. And we are gonna do it with with proxy geometry, and then we can switch it to the high res. So we have just to import our high res geometry by using an object merge. Let's go to the house geo, and I need this old wall. Okay, so since this doesn't have a density attribute, as you can see, even if I impact this geometry, I have to transfer it from the proxy geometry. So let's do it by using an attribute transfer to this high res coming from the low res. And I want to transfer the density, which is a point attribute now that we have promoted it. So I'm going to leave this threshold as it is, and let's see if we are transferring this density properly. Okay, here we go. Perfect. Now we can assemble this. So let's drop down an assemble node. I don't want to override the name attribute. I want to create back geometry from it. And I'm going to need the attributes I had. So let's transfer them again and duplicate this assemble to the high-res pieces. Cool. So as I said, we're going to start creating the workflow with the proxy geometry, and then we're going to switch to the high-res. So let's drop down a switch node, and I call it low to res to high res. Okay, and we can go one step further, and I think it's a good idea if we start working with just one piece of this geometry. So I can grab, for example, yeah, I like this one because we can add some fracture to it, and also is hitting the ground. So I think this one is going to be cool. So let's grab this piece, non-selected, and since the name is the same, we can add it to the high-res. But of course, this has no animation. It's a static geometry. Perfect. Actually, it looks like these high-res pieces have some animation, and if you look closer, it looks like it's happening on the density attribute. So let's just time shift this to the starting frame here. Sorry for these viewport issues. Let's set this to F start. Okay, so now we can switch from low to res geo. Great. So let's add the fractures to this low res geo. And as you know, we have to unpack this before. This time I'm going to transfer the density. And since this have also animation, we can time shift this again to $F start. And we can create a VDB from polygons using the density attribute, which is here, density. We can also add some noise to it. So let's drop down a volume bob. I'm doing the same as the last week, as you can see. This is why I'm going as fast as possible. Multiply this. Change the amplitude and frequency, something like this. Let's add a scatter node, and remember to turn off the reactive duration. And as you can see, sometimes this is a required step, because as you can see, we have nonsense points scattered out of this geometry. So let's just turn off this, and this is going to be fixed. I don't want to have a constant point, so let's turn this off, and let's use the density. Maybe we'll start with 50, and now we're going to fracture this. Here we go. Let me see the new fractures. Okay. I'm looking. It looks like it's not fracturing. Let me see what's going on. This is the new piece. This is the other one. Okay, so it looks like this is fracturing, but I don't know why I can visualize this. Let me, this is the name. Yeah, okay, we are having issues here because we are visualizing the old name attribute, which is this cluster wall 20. So this is a required step. Before doing the new fracture, we should save this old attribute to a new one. So let's create a primitive wrangle, because I want to save this attribute, and I'm gonna do it to, I'm gonna save it to old name, for example. This is the new string attribute, and this is gonna be the same as the name. Now we are just duplicating this attribute, and now I can delete it because we're gonna create a new one in a second. So let's delete this name attribute. Here we go. And now, let me see, we still have this name attribute. Oh, this is the points. And this is creating the name on the primitives. So let me just, I like this name. Let me delete this one. And here we go. Okay, now that we have this, actually I think I had to delete the point attributes, not the name attributes. Yeah. We can call this Voronoi fracture pieces to sub. Also the inside group, inside sub. And if you want to add some clusters, you can do it right in this step. I will leave this to you. And here we can also add the interior detail to these new pieces. But remember, it has to be applied on the same group created by this Voronoi fracture. So let's just copy parameter and paste it here. Let's explode this. Let me lower the size. Something like this. Okay. Okay, this is fine. So now what I want to do is to transfer the old animation, the old transformation from the geometry simulation to this new piece. Let's turn off the visualization of the pieces. And of course, I'm gonna work with the proxy geometry. So at this point, we need to convex the composition this again. I don't need this segment attribute, and assemble this because we need to use back geometry. And yeah, that should be fine. So let's drop down the transform pieces. And this is the geometry we want to move, this piece. So I'm going to plug it here, geometry to transform. And I want to use this one. I want to transfer this animation from this geometry to the fractured one. So let's connect this to this last. Now let's see if this is working. Yeah, it looks like it's working. But as soon as disable, I bypass this last node, you will see that we were making a mistake. And maybe you can figure out why that wasn't working. On the template, I have the geometry moving, and as you can see, the new fractured pieces, which are these ones, these are the old ones, and these are the new ones. So this new one, they are not getting the transformation from the old ones. Why is this happening? Firstly, we don't have the same name attribute from here to these pieces. They have different values. So what we need to do is to use this old name attribute. Let me rename this to set old name. So what I'm going to do is to use an attribute wrangle here, and I'm going to call this, I want the name to be in the old name attribute. Because I want to transfer the movement of the old pieces, the ones that are not fractured, to these new ones. And to do so, I need to use the old name. So let's transfer the old name. And this attribute, this name attribute, has to match. So as you can see, here we have this old name attribute on points, and here we have this old name attribute on primitives. So we can just promote this one from primitive to points. And last step is to change this attribute to old name. As you can see, we have some problem, and this is because we need to fill the third input. As you can see here, it asks for the rest points, so we can time shift the moving pieces to the first frame. And here we go. This is the geometry with the new fractures having the animation of the old geometry. And we are connecting them by the old name attribute. And let me show you what would happen if we didn't fix this gotcha. If I disable this time shift and this copy, attribute copy, I go back here to transform pieces. If I give this a frame, let's see what happens. It messes our pivot. So this is why it's important to fix this previous step. So let's do it again. Okay. And let me summarize again what we did here, because it's a little bit complicated. First, we have the proxy geometry. With these transform pieces, we are getting the transformations from the points, because this is a very, very optimal way to work. Then we unpack this, and this step is just to transfer the density attribute to the higher geo. This is what I'm doing here for later purposes. And here I'm fixing the pivot that changes on the second frame. Okay. Remember that in all the steps we are gonna need all the attributes. So either in the impact and the assemble, we need to transfer them. Here we can switch between low and res pieces, and in this tree of nodes, we are adding the new fractures to these pieces. So to do so, we have to unpack them. We have to set these pieces to the first frame, and we fracture them using the same method as we did last week. And because we know that we have to transfer these non-fractured pieces to the old one, we have to match the name attribute. So that's why we create a new old name. Then I'm deleting the name attribute here because I no longer need it, and we can fracture these pieces. So the old name attribute is going to transfer throughout this process. Now we can add the RVD interior detail to this, but we're going to work with the proxy geometry. So again, we have to convex the composition this, assemble, transferring the old name, and since we are having we have a point old name attribute here, this one, we have to match it here as well. So that's why I'm promoting it. And then we're using transfer pieces, but this time we need to set a rest position to the third input. So now the idea is to use this animated geometry to have total control on when and where to activate these new pieces that we have here. So we'll need to override the animated and active attributes on the RVD packed object in order to go from static to active objects. And to do so, we are gonna drive this active attribute using the DOP import records, because we want to active the set an active attribute to 1 each time this piece has a collision. So let's go start by unpacking this, because I want to transfer the impulse attribute to drive this active. So also we are going to need the records, which is in this same network, but it's it's on the top of it. So I think it's better if we just call it from this object merge. So let's type the records. And as you can see, we have a lot of points, and this is because we are importing the records not only of the wall, but of the other elements. Since we are only gonna work with the wall, let's delete all the other elements by typing object name equals to wall. These are points not selected. So now we are working only with wall element. Perfect. And let me check if we have a, yeah, I want to transfer this impulse to these pieces. And as always, let's do it by transfer swap. Let's connect this and this. And let's set this to impulse. Let me see what I get. I can control click this to see the impulse attribute. And maybe change the threshold to 0.5. Let me see this piece. Okay. I think this is exactly what I want. So I need this active, this impulse attribute is we are going to use it to set an active attribute to 1. Therefore, we need this to be persistent, which means that we need a solver. So let's fetch a solver here. Let's connect this first input to the geometry and the second to the records. And I'm going to use this attribute transfer. So I cut it and I paste it inside. And I don't want this impulse to overwrite the one of the previous frame. Instead, I want them to add to the other. So what I want to do is transfer first using these nodes, which they have nothing to do with this dot import. Now we have the same thing that we had in this level, but inside. And then I need the wrangle here. And I'm going to connect this first input here and the second input here, because I will type this following expression. I want the impulse attribute to be added every frame, and I want to take the one from the first input, second input, which is the number 1. So I'm taking this impulse attribute to every point, because we have the same number of points here and here. Let's jump back and let's see what we get. As you can see, this looks like is persistent, but we lost the animation. So we can just recover it by using an attribute copy. Let's plug the first input here and the second one here. And I want this attribute to be the position. So let's see now. Here we go. Let me check this. It's barely visible because this impulse attribute is it has super high values. So since this is set to automatically, it's hard for it to set a minimum and maximum values, because we're going from 0 to 30,000. So as you can guess, we have to fit this. So let's use a wrangle, and I'm gonna say I would like to override this impulse attribute, so I'm gonna just fit the same impulse attribute. Let's say from 0 to 1000. This is the top number I'm looking for, 201. And here we go. Then you can see we have persistent impacts like this one. Perfect. Time to assemble this. Don't override the name, just pack the geometry. And of course, I don't want to lose this impulse attribute, so let's transfer it. Here it is. And then we need to write an expression to use this impulse attribute to create a new active attribute. So let's write, let's drop down a wrangle again. And I will say, first, I want all these pieces to be inactive. Inactive means that it doesn't mean that they're going to be still. They will have animation if I set this to 1. If you remember, those are the attributes we can override in the RBDPath object. These ones. So I'm working with the active and animated. Okay. Then, if the impulse is bigger than some value, then I'm going to set this active to 1, and I'm going to set this animated to 0, because I don't want to follow this animation anymore. I want this piece to be a RB object and have collisions with other pieces, have gravity, and so on. Cool, we can create the channel, and as always, we can use a blast to debug this. So I'm going to say active equals 0, points. Let me set this to template. And let me see, I'm going to take a look at this piece of chunk. Here we go. As you can see, this should have a fracture here, and when it collides, I'm breaking this fracture. And I can tweak this slider to set the number of pieces I want to break based on the impulse. So this is great. Let's leave it like this. And what I need now is to copy this active and animated attribute to the third geometry. So let's drop down these transform pieces, attribute copy again from this. I'm gonna copy this active and animated attribute from these pieces to this one. That's pretty much it. So let's set this into a network. Make sure that we have packed fragments. Let's dive inside, and I'm going to need the first context geometry. I will use a gravity, rigid body solver. I'm going to use a ground plane. Now, actually, let me copy and paste the ground plane we had before, because if you remember, we have to fix some the Y component. So I'm gonna maximize this by pressing Ctrl V. I think, yeah. And I'm gonna copy the collision geo as well, which is the sphere. So let's go back to our source fractures, copy this here, and merge it with the RB object. Okay. I think that's all. Maybe we can take a look at the representation guide of this. Be aware of checking this out. And let's give it a try. As it is, by default. Oh, of course, we have to override this attribute. So let's check this on, let's turn this on, and I only need to override the active and animated. I did it on shop level. I did it here. So let's go again here. Let's press play. And here we go. Let me check this piece here because I was interested on this one. And if you remember this chunk, this big chunk here, I'm getting new pieces, I'm getting new pieces broken wherever I have the impacts. And this is going super fast because this is reading an already cached geometry, which is animated geometry, and I only have few of them activated. I think it's cool, but we can go one step further, and you can maybe try to convert this to box just to gain some speed, because at this level of detail, I think we're not gonna notice the comic school option. Let me see. It should go faster, so it's up to you which one of these geometry representation you want to use. Okay, so let's import this with the .import sub. And if you remember, we have a preset here, so I'm going to use it this time. I don't need the wall, so I'm going to type everything RBD, which is the wall. And now, as we are working with proxy geometry, we have to transfer this animation, this simulation, to the high-res geo. So let's again drop down the transform pieces, connect these template points, and what I need is this one. But of course I need to be assembled. So let's stop this cooking, and I'm going to create an assemble node, check the back geometry. Now I'm going to allow this to create the interior detail, and let's see if this is working. It looks so. Yeah, here we go. And now we're using this name attribute because it's the one we created here, so it's fine. But we're not done yet. As you remember, we are working with a proxy geometry. We are doing all these steps. Even though we are adding high-res geometry, now we have to switch this to high-res geometry. So this workflow allows you to quickly set a simulation. You have to take this time to improve the simulation, to add more or less pieces, to play with the scatter, to play with the impulse, with the threshold. And once you're happy, you only need to switch this to high-res geometry. But of course, this is going to take much more time. So I'm going to give this the input 1, and I'm going to pause this until this is cooked. Hello again. So it took like 2 minutes to compute the Voronoi fracture with the high-res geo. But once this was done, remember we are using convex decomposition of this, so all of this workflow is going as fast as before. And also it took me like 20 seconds to simulate this. And as you can see, we have crazy detail on each one of these little pieces that are coming from the main simulation. Also remember that there are several steps where you should add you should cache the geometry. For example, after doing the Voronoi fracture, it will be a good practice to cache this. So you don't need to do this fracture every time you open the scene and try new values here and so on. So let's just finish this by creating a null node here. I'm going to call this out wall. You could also add a file cache here. And now let me show you how I will add this to the main simulation. I'm going to call this out wall into the subfracture network, which is here. And what I'm going to do is to transform all these elements but the wall, because right now I have the high-res simulation of the wall in other place, which is here. So let's merge this together, and I'm going to pause this and I'm going to show you a quick flipbook. So this is the result. And as you can see, we can add some drag here because maybe this is too aggressive. But what is really interesting about it is to take a closer look at it and see how the new pieces are behaving as expected. We have a lot of new geometry detail, interior detail to all of these pieces. We have bending. So I think this is great. And of course, we expect from you guys to improve this simulation since you have a lot more time. And remember also to work organized, to have whatever you need inside subnetworks. You can color the things, you have to name all the nodes properly, but for the sake of the speed, I'm not doing this. Also, you can apply the same method. I would say not to the wood, because maybe the wood pieces are too thin and too small, but maybe you can apply the same method to the roof. That would be great. So let's go ahead and talk about debris. So before introducing you the debris system, it's always a good practice to cache the elements that we potentially could need for the further creation, further workflows. In this case, I already know which elements are they, but if you are working on something and you feel that every time that you are changing one parameter or creating new nodes, you have to wait until something is cooked, definitely you have to cache that that node, 3 nodes before reaching that step. So that's exactly what we are about to do, and I'm gonna just copy this file cache because I have the type, element, and version here, and this is gonna be useful. So let's jump back to the object level, go to the house of fractures, and the first element I'm going to cache is the RBD interior detail high-res geo output, which is this one. So let's just paste this cache here, and I'm gonna say this is the geo wall fracture. So let's save this file into, this is a geo. Let's call it wall fracture version 1. Let's delete this because it's a still frame and set this to current frame. Okay, now I can save this. Cool. The other element I'm gonna need to create the debris is the proxy output of this, because this element has all the pieces from where we are gonna source debris. So let's just paste again this file cache, plug it here. It's gonna be our geo wall fracture proxy. So let's type the same words here, geo wall fracture proxy, and delete this and current frame as well. I can save this, and let's create a null here, which is going to be our geo wall proxy. Great. Lastly, I need one more element to be cached, and this is the simulation, which is a very common element to be cached. You always want to cache your simulation. So let's again drop down our file cache and say this is going to be our sim wall proxy. And this time is a sim type. This could be, for example, wall proxy and 001. And now I can save this to disk. But since I have already do it, I can just load it. And remember, it's a nice idea, it's a very good idea if you want to save some hard drive space, to save this as create points to represent objects, because if you do so, you can use the transfer pieces node to transfer this this animation of these pieces to the high-res geo. So here we have the high-res geo with all the interior detail elements, but I also need another thing, and it's this kind of simulation, but with the proxy geo. So instead of taking the high-res geo, which is this one, what I'm going to take is the not lower geo, but the geometry without interior detail. So let's change this assemble to the to this output, and I will call this as old wall animation. Here we go. You can see we have much more interior detail here. Cool. So let's jump back, and now time to create our geo node. To start with the breeze system, I'm going to call this as the breeze, dive inside. And first thing I'm going to need is this new wall out wall animation output. So let's go and call it here with this. Okay. So a little heads up before starting the breeze creation. Here you're going to see a bunch of new methods, techniques, and scripts to create and source this debris from this geometry. But also, we're going to go back and grab old methods and old techniques that we already shown you. So I think it's pointless and a waste of time if I create those from scratch, node by node, and I write each one of those scripts because you already know it. So instead of doing that, I'm gonna show you everything as usual if the workflow is new for you. But if you can just go back and watch again the earlier videos, I'm gonna just pause the video and copy and paste, and I will show you quickly all the stuff I've done. So that being said, let's start by, as you can see, we have a proper called the old wall animation. So now I need to compute. Let's compute the velocity again, just in case. And as you can see, this is giving me an error, and this is a gotcha. And I wanted to show you actually because. As you can see, this is what it's saying is unable to read this file. So what is happening here? This is using the previous frame to compute the velocity. But since we don't have any previous frame, we have to either check this, set this to forward difference. If we are computing the velocity, we have to set this to forward difference. Or we can also evaluate this velocity calculation within frame range. Now we have the node working properly. So first step is to create an ID to all of these new pieces. So let's write this down, and now I'm gonna use the velocity to delete the pieces I'm not interested in sourcing debris, and those are the ones static. The debris creation is nothing but adding some filters, some layers, using the attributes from these pieces to get the proper source. So let's maybe start by renaming this node. Create ID attribute, and this is going to be remove by velocity. And what I need here is to call a new float attribute, temporarily float attribute, and this is going to be the length of the velocity vector. As always, if you want to see this attribute on your spreadsheet, you have to create, you have to cast it. And using the underscore before, it's going to make this attribute go to the first place. So as you can see, we have this the velocity vector, the length of this velocity vector correctly computed. So let's delete this and let's call an expression. And I'm going to say if this length is less than some minimum value, let's just remove this point. Now if I give to this parameter some value, all these points are going to be removed if they are if they have less velocity than this value. So this could be a first step. And remember that all of this is going to turn out to points, and these points we are going to use it to source a pop network, and then we will have a debris from it. So definitely you can see we have to remove much more of them, and we have to set where on these pieces we want to emit from. For example, it's not realistic if the emission goes from the surface of these pieces, but it could be a good idea if they are being emitted from the inside. And also, we don't want to emit forever. We want to stop the emission at some point. So to do so, we can create a new age attribute. Let's start by creating this age. I can just create an age attribute by doing this, and then we need a solver because I want to add one unit to this age attribute to every frame. So I'm gonna need first to copy this age attribute from the previous frame to the actual frame using an attribute copy, and I will use the ID attribute because I have it, and therefore we can make the pieces match with it. Remember, the attribute name is age, and once this is copied, we have to update this attribute. So we can add one unit to this age by using this expression. Let's output this, and let me see if this is working. Yeah. As you can see here in the spreadsheet, we have different ages depending on the life of each one of these pieces. So would be a good idea. For example, take a look at this piece here. If this piece has a life or has an age bigger than some value, just delete it because we don't want to emit from it forever. And also, we can add some variation to these ages. So let's just create a wrangle node, and I'm going to call it add random age variation. And first, I need some random attribute, but I need an integer one. So let's say integer rand age is equal to feather1 random of. I'm going to use the ID just in case these points are being removed at some point, and maybe go from 10 to 15. This is complaining because we are creating an integer and this is outcoming a float, so let's just transform it to integer. Better, and then it goes the condition. Let's say if age is bigger than this random value I just created, just remove the point. And here we go. As you can see, these particles are being removed. But this is cool because when this system notice that the particle has again some velocity, it's gonna create new debris from it, as you can see here. Also, I want to add one more line to this because, as you can see, we have a lot of particles of the first frame. So we can say, for example, check this condition and check another condition. This will be if age is less than, let's say, 2 or 3. Yeah, I think 2 is fine. Then we can fix the amount of particles being created in the first frames. Perfect. Now, as I said, this debris shouldn't be sorted from the surface of each one of these particles, because I think it's realistic if we get this debris from the inside. Let's go to the simulation again, and if I give it some frames, we want to emit from these cracks, from these interior surfaces. And this is why I needed this high-res geometry wall animation, because I have the inside group here, not in the proxy one, because the convex decomposition kills the group. So let's unpack this. I will transfer the velocity and the age, just in case I need it later on. And let's just blast the inside groups by using a blast node. Okay, let's set this to inside. As you can see, we have 2 groups, so I'm gonna delete both of them and unselected. And all of this geometry belongs to the inside group. And now I will show you another cool technique. We want to use a scatter to source some points from this geometry, but of course I don't want a uniform number of points every frame, and of course I don't want to relax the iteration. What I need is some density value, and this is because I promoted the edge through this unpack node, I could use the edge to drive this density, meaning that I can divide some value, some initial value, by the age. So this value is gonna eventually go to 0 or to a very low value. So what I need is to set this new value. And since this is asking for a density attribute, let's just call it density. Density attribute. So what I need is to use a float density attribute. I need some initial value, which could be 1000 for example, and divided by age. And as you can see, if I go to the first frame, this geometry is created here. Let me check for yeah, we don't have any age of 1 because we deleted them by using the this one, yeah, this condition. But as you can see, if the age of is 2, this value of 1000 is gonna be divided by 2. If I give more another frame, it's gonna be divided by 3, the ones who have an age of 3, and so on and so forth. So now that we have a density value, let's just scale it from here. I think this is probably too much, so we can lower the density, and we can also change the seed to every frame. Let's see what we get. At first we have a bunch of points, but as soon as we are going forward, the density is becoming lower and lower. Great. Last thing before caching this to disk, I want to add some variation here, but actually let me show you why I need this. So let's create a pop network out of this, dive inside, and let's super quickly set this up. So I want all points coming from the first geometry context. I don't want them to die never, so I just increased the life expectancy. And let's add some collision geometry, which I already have on the clipboard, so I just want to paste it because this ground plane, as you can remember, needs this value to be fixed, to be placed in the proper space. So let's merge all of this together. And now I can maybe set the physical bounce to 0, the friction to 1, and let's hit play. Here we go. Maybe let me set to this to add some inherent velocity. Maybe you can check this 2.9, lower this. And I also want to set this interpolation source to forward and match point velocity. Let me see now. Okay, as you can see, this simulation is kind of boring because this is being emitted at each frame. So there is a method to break these initial points, and it's super simple. Let me add a attribute wrangle just after the scatter, and if I go here, we want to break, for example, all of this point shape because it's clearly looking the shape of the piece, but we want, the trick is to use the velocity to do so. I want to add some random position using this velocity. So what we need is to set this position and subtracted the velocity. But I want this velocity to be normalized, so I can create a normalized vector of this velocity. So I can be assured this will never be greater, the length of this velocity is never greater than 1. And then I can subtract this velocity by multiplying it by some number. Now, if I bump up this value, you can see we are moving these points to the velocity direction. So now, as you can imagine, we would like to randomize this. So let's do it by creating a float. We want to randomize using the frame number. So we can call the frame plus some seed and call the random value using just the ptnum plus some seed. And now I can use this to add to the multiply expression. And here you go. Of course, if I change the seed, this is going to change. Something like this. Okay, let's organize this by pressing L. And we can cache this. I don't know if I still have the file cache on the clipboard. No. So let me quickly search one file cache. This one. Go back here and paste it. This is not a simulation, this is a source, so we can save this as source debris, and I think this is fine. So let's save it. Okay, this is done. Let me show you what we have so far. This is the source, and now we have to plug this into the pop network. So this is not going to be the bridge system, but we can use this to create dust from it. So let me call this as pop to get the particles. And of course, you can add more variation here. You can add some drag, some wind, whatever you like. And let's set this to out dust. And this is ready for rendering. Okay, let's keep moving. The next step is to take all of these points, and I want to instance some geometry in each one of them, because I want to show you a trick to use a rigid body solver and use a pop source to instance and to source geometry. To do so, we need to go back to the first, second, or third week, and we are going to use the same method we used to copy instant geometry to each one of these points using the randomize function, and for each method, the compile method. So before starting, let's just, because we don't know if this is gonna work, and it's also a good idea to remove some random points if we have a lot, just to test with them, and then to extrapolate it to the other ones. So what I'm gonna do is first fracture some geometry, create back pieces, and then I want to grab the compile for each method to randomly instance them into these points. And because you have already done this, I'm gonna pause this video, create this method, and I'm gonna show you quickly what I've done. Okay, this is done, and as you can see, you can maybe recognize some elements here. This for each, as you may imagine, is instancing randomly the geometry, the back geometry to these points. So we have the points coming from the right and the geometry coming from the left. We ended here. We have the points to instance the bridge here. And let me go to the very first node of this. This time I used a platonic object because I like these edges. And I also used the RBD material fracture to create the fractures out of this. And let me show you step by step. As you can see, we can get some nice details from this fracture. The values I set to this node is I did 3 fracture levels. You can tweak the scatter points, you can tweak the frequency, whatever you want. And then I add some chipping, which is gonna create these little pieces out of these chunks. I add some detail. But as you can imagine, we are not gonna source these pieces to the simulation, to the rigid body solver. As you can see, we have some edge detail, some interior detail, and I don't need constraints. So next step was to assemble these pieces, as always, and I wanted to get rid of the very, very small pieces because, as you know, they can cause problems to our simulation. So I just went for each piece, unpacked them. I used the measure sub to get the volume and promote it to from primitive to detail with this method to have the volume, the sum of these volumes here, and then I promote it again to points. So once this is done, I can delete the lower pieces, as you can see here. Before and after. And let's assemble this again. Don't worry, it's time to override the name attribute. And I think this is, I don't need this. Yeah. So I stored these high resolution pieces on my left after going for each one of them and transform to the center, as you already know. And I did the same, but since these pieces are super small, are intended to be super small because they are debris, I thought it could be a good idea to make boxes out of them to send to the simulation. So if you connect a box here, it's the same as connecting a bound sub. But note that every time we connect a box here, it's gonna break the back geometry. So first I send this to the origin using this, you already seen this, and then I pack this again. So now I have on one hand this, and on the other hand this. Cool. As you remember, to use this for each compile method, we need an ID. We are setting a random ID based on the number of points, or sorry, the number of, actually I have to change this, on the number of packed primitives we have, this one. It means that if I have a total of 384 primitives to be randomly instanced on these points, I need this value. So here I'm setting a random ID to all of these points, and this ID is the one I need to do this for each compile operation. But, and this is why I added this enumerate sub here. After doing this operation, when the simulation is done, what we are going to import is cubes. And all of these cubes, we need to convert them to the higher geometry. So I need another attribute because I can't use the ID since it's going to be overwritten here. To do so, I just used this enumerate sub, set 2 points in each one of them. So this is creating the ID, and this is creating the index. You're gonna see in a bit how we use this index. This is what we done on the car simulation, the cars exercise, and as you can see, if I wireframe this, we are instancing random cubes on each one of these points. And this is a good idea, and you can later on compare the two methods, the one using cubes and the one using this geometry, because as we are instancing this very low res geo to this, and we are playing with in the simulation, this is going to be super fast. Okay, so now I get rid of the, as usual, the attributes I no longer need. And before sending this to the DOP network, we still have a problem here. As I told you, I want to use these cubes to drive a rigid body simulation. But if you remember, rigid bodies needs a name attribute, and we don't have any name attribute here. So I guess you are thinking why you don't create a name attribute before instancing these pieces to points, and we could do so. Let me just this is back geometry, so I'm creating a name attribute here for each one of these pieces. And if I go here, let me show you why this is not going to work. If I sort this by the name, you can see we are searching pieces with the same name attribute. And this is a huge mistake, as you can probably see. So we have to create our own name attribute out of this. But how we can do it? If you take a look at these pieces, you can see each one of them varies on every frame. So this is giving us a hint of what can we use. We need to use the number of the frame and the number of the point to create a unique name attribute. Cool, so let's do so by dropping down an attribute wrangle. And let's set this name attribute. This is a string, so I have to type s before, equals name equals piece plus this function I to a. It means convert the integer to the string. I need the frame number so I can use the frame. But remember, this is a float, so I have to convert it to an integer. Plus, we can add some. No, let me show you step by step what we are doing here. This is the name attribute. So far, so good. Now we can add some underscore. And now I want to add the piece point number. So again, integer to string ptnum. And we will go. In each frame, we're going to have unique named pieces. This should be enough, so let's go ahead and create the network. I just want to test if this is working. Let's dive inside and make some space here. I'm gonna call this back object, need a reachable dissolver. We can use a gravity here. And one method to call these pieces, each frame, if you can see, if I set this to first contact geometry and I press play, let me see, is this geometry packed? Let me see, okay. Okay, we are not getting anything because this is asking for the first frame to be solved. So we have to change the start frame of the simulation to the frame where we have the pieces, which is the 22. So let's set this to 22. Let's try it again. Here we go. So as you can see, if I give to this more frames, we are not sourcing pieces at each frame. To do so, we have to change this creation frame. We have to delete this expression by Ctrl-Shift, left-click, and type $F. So now it's going to create an object to each frame, at each frame. So let's set. Okay, let's play this, and now you can see this looks like working, but this workflow is not very optimal because, as you can see, we are having a lot of objects, which means we have a lot of information. A cool trick to use instead of this is to, let me set this by default, is to use a pop source. If I plug this into third input, I can call the geometry from the first context geometry from the first input using the all geometry. So I'm going to set this to all geometry, and let's maybe set the life expectancy to forever. I don't want these pieces to die. And let's see what happened now. I'm going to save this, hit play, and first frame. Second, this is adding new pieces to our simulation without adding new objects, which is super great. Cool. Let me play this. I don't know in which direction are they subbing. Yeah, okay. Here we go. As you can see, we have a few ones that are exploding. So let's fix this by using pop speed limit. Maximum speed to, for example, 15. And I would like to use a pop drag to set the air resistance to the pieces, but I had problems with this node. So for now, I'm not going to recommend it. Instead, I'm going to use something which does the same using a geometry wrangle. And I can call the velocity and multiply it by 90%. So this is going to reduce the velocity 10% at each substep. And of course, we can add more variation to this, but I'm going to leave it to you. Perfect. Let's now copy and paste the ground plane again. Let's see if we fix the velocity issues. It looks so. So the next step is to call the wall simulation to use it as a static object. So we need the wall proxy geometry, which is on the house of fracture. This one, no, I need the geo one. So, and also we need the points that are representing the simulation. And we could use a transform pieces here to transfer the animation from the points to this proxy geometry. That could work, but since this is intended to be debris, and debris are very small pieces, I think we can even optimize more these pieces. And I'm going to show you a trick to do so. So let's call a for each primitive loop. And what I want to do is to add a box for each one of these pieces. And we're going to simulate with this box, which is going to be a very optimal way to do this step. So let's call a box. And this time, what I'll do is if I plug an add node here and I delete everything but the points, I will get the centroid of each one of these pieces. So I can copy 2 points, this geometry, to the pieces. And of course, we need backed objects. But as you can see, we need somehow to get the scale of each one of these pieces. And we need that scale to be transferred to the box. So let's use the attribute wrangle. And I'm going to type vector scale. And this one is this attribute scale is like normal or orient or p-scale is the kind of attribute that when you add or you instance some geometry to it, it's going to be recognized. So I will get the pivot size. So of the input 0, which is the incoming geometry. And as you can see, we have a vector here, which is the same values as we have here. And then when I copy the boxes to it, the boxes will inherit this scale. Perfect. So we are going to use this as a RBD packed objects. I don't need this scale attribute anymore, so I can delete it. And I think it's a good time to file cache this, and I'm gonna simply stash for the sake of the speed. And here you go. We are getting the wall simulation with the subfractures, but this time with cubes. So let's end with plug into the second input. Let's dive inside the network. Remember, this simulation is starting at frame 22. So now what I have to do is to call this static object, which is going to be animated. So let's plug this here. Let's set this to animated static object and second context. Let's say wall static. And let's go to the first frame where we have something to simulate with, because I want to take a look at the geometry representation. First of the debris. We have to inherit the point velocity because we have point velocity here. And we need this to be a convex hull. This is fine per set of connected primitives. And set the collision padding to 0, because otherwise you will get these collisions, and this is going to add more geometry to our pieces. So this is fine. I'm happy with this. So let's take a look at the wall. I'm going to turn off display geometry. I'm going to turn on guide geometry. Same, set this on. And I will set the collision padding to 0 again. And that's pretty much it. We can even lower the sub-steps because this will give us faster simulation. So let's now import this with a .import node. Let's set this using our preset and call the debris. There they are. And let's see how fast is this simulating. I think the direction is over there. So I'm gonna hit play. And there you go. Note that this is not a particle simulation, this is a rigid body simulation, so it's pretty fast. Alright, so let's end up this with using this same exact method to instance the high-res geometry to each one of these points. So I'm going to pause the video, I'm going to copy all of this and connect it here. Or now maybe actually I can do it using this for each compile node. Let me see. Let's connect this to the enumerate. And we don't need all these attributes, so let's use an attribute rename here. And I only want to keep with few ones. I only need the orient, the pivot, and the index. And this time we have to do the same operation, but remember we have an index attribute. So this time I'm gonna set this attribute to index. And same with this. Okay, let me see. Yes, here you go. We have high-res geometry, debris representation on each one of these cubes. And we are saving a lot of time by simulating with these cubes. Perfect, you can also add the sphere here, but I will continue by adding another very useful node, because as you can see, we have a lot of points here in the viewport, and this could cause issues to our graphic cards. So a very good workflow or good practice is to set this to Pack Edit and change the display to centroid. So now we are changing each one of these high-res pieces to a point. But when we want to render this, this is not going to be rendered as points, but as the high-res pieces. So this is super cool to me. Perfect. Now let's create an attribute delete here again, and we can delete index, orient, pivot. Of course, we have to file cache this using my custom file cache. We can save this as this is a simulation, so simulation debris, sim debris 001. Remember, this is going to create our folders, and we are ready to export this as out debris. Okay, guys, so that's pretty much it for this week. I hope you understood all this process, all the steps we did. And this is a very, very quick raw render of all these elements put together. As you can see here, I've fetched the debris, I gave them some color, same with the subfractures. And of course, if I have to render these subfractures, I have to bypass the wall, because this is another simulation of these walls. We don't want to override it. And this is the dust pass with the particles. I gave them some randomized p-scale, some random color, and if we look closer, we can appreciate all of this debris, the dust, and the interior detail of these pieces. And it's all to you to play with everything we've seen so far to get a much nicer and realistic simulation than this. And remember, you can add textures, motion blur, you can add more layers of debris, dust, constraints, etc. In next module, we'll add some smoke to it. But for now, see you in the next week, and thanks for watching.